Section 13.5 is going to wrap up our discussion about factoring, and we're going to be discussing factoring special cases. Just so your notes are complete, I know we wrote this in the previous section, but sometimes I like writing redundant notes. First step for factoring was GCF. Second step for factoring was to see if we could do grouping. When I talk about grouping, this is the grouping I'm talking about right here. When you have four terms and you cut it down the middle, that's technically grouping, right? We could do grouping within trinomial factoring, but we had a lesson where it was its own separate problem too. We've talked a lot about trinomials up to this point, and the last step for factoring are called special cases. And there's three different types of special cases we'll go over tonight. Just like before, we factor going in this direction. So even if you see something that looks like a special case, first thing we want to do is take out a GCF. And the three special cases that we could see are if you see something squared plus 2 times the first and last plus the last squared, we could write this as x plus y times itself, or just x plus y times x plus y. And I'm going to give you examples of all of these too. So for right now, let's just write the formulas down, and then I'll show you how to apply them. Second special case is if you have something squared minus 2 times the first and last plus the last squared, we get x minus y to the second power. And again, that second power just means we could write x plus y times x plus y, or obviously with the x minus y. And then the last type of special case that we'll see is if we have a difference of perfect squares. This is called the difference of perfect squares. And we could write this just as the first plus the second times the first minus the second. Let's take a look at some examples. Just like before, the directions are just going to ask you to factor completely. And let's start with x squared plus 16 plus 64. When we look at the special cases, first thing I want you to recognize is that x squared is just the same thing as x times itself. 64 is the same thing as 8 times itself. So if you have a first term that's a perfect square and a last term that's a perfect square, you might have a special case if the middle term is 2 times the first and the second. And it looks like that's exactly what we have here. 16 is the same thing as 2 times 8 times x. So what we could do is we could just say that this factors to be x plus 8 squared, and you're done. If we recognize the first term is a perfect square, last term is a perfect square, and the middle term is 2 times the first and last, we could just use that formula. We could have also done this using trinomial. So we just do 1 times 64. I have to add up to 16, so that's 8 and 8. So we could have written x squared plus 8x plus 8x plus 64. Cut it down the middle. And you get exactly the same answer. X plus 8 times x plus 8 is the same thing as x plus 8 squared. But doing this shortcut, we were done in 10 seconds. Right, this other technique, it still works, but obviously it just takes a little longer. The key is the first and the last term special, are they perfect squares? What about if we had a problem like this? X squared minus 6x plus 9. There's no GCF. Can't do grouping because there are 3 terms. We could do trinomials, but one thing that I recognize is the first term is just x times itself. 9 is just 3 times itself. And the middle term is negative 2 times x times 3. So it looks like we have another special case here. And which means we could just write this x minus 3 to the second power. First term minus the second term. Make it a little more challenging. What if we had 4x squared plus 20x plus 25? If you don't want to remember the special cases, you don't have to. You could do this using trinomials. You'll wind up with big numbers. But the cool thing about special cases is this first term is the same thing as just 2x squared. 25 is the same thing as just 5 squared. So we could use the special case formula as long as the middle is just 2 times 2x times 5. And 20 is the same thing as 4x times 5. So because it works out, we don't have to do trinomials. We could just say this factors to be 2x plus 5 to the second power. Why don't you take a minute and see if you can figure this out if it's 9x to the second minus 24xy plus 16y squared. So see if this is a perfect case by figuring out what the first term is squared, the last term is squared, and then see if the middle is negative 2 times the first and the last. So it looks like it is. 9x squared is the same as 3x times itself. 16y squared is the same as 4y times itself. And if we put 3x and 4y in the middle and multiply it by 2, we get 24xy, which means we could just factor this simply by doing 3x minus 4y to the second. Like that. What if we had x squared minus 4? Well, x to the second is really the same thing as just x times itself. 4 is the same thing as just 2 times itself. So if you go back to our special cases, it looks like this one. You have something squared minus something squared. We could just write it as the first plus the second times the first minus the second. So x squared minus y squared, the formula is x plus y times x minus y. In this case, it's just x plus 2 times x minus 2. Similarly, if we had 9x squared minus 1, this is the same thing as just 3x to the second minus 1 to the second. But according to the formula, we just write the first plus the second times the first minus the second. One thing I will point out is we were talking a little bit before about there being multiple formulas for things, and I told you I'm not really a fan of trying to remember all these different formulas. You could use trinomial factoring for this. So if you wrote 9x squared plus 0x minus 1, there'd really be no reason to do this. It's much faster using special cases. But if you put 0x in the middle, we're looking for numbers that multiply to be -9 and add up to be 0. So 3 and -3. You can write this 9x squared plus 3x minus 1. Cutting it down the middle, taking out a -1. You can see we get exactly the same thing. But it's just a lot faster if you recognize the special case. What do you guys think? Do you agree? I think that's the way to go. A couple more here. What if we had 18x to the second minus 50? Well, what squared is 18? Other than the square root of 18. Problem is, you can't just go straight to special cases. Can we take something out of this first? 2, right? We can take out a 2 and a 2. And we get 9x squared minus 25. That looks like a special case. We just had to take the GCF out first. But now 9x squared is the same thing as 3x to the second. 25 is the same thing as 5 to the second. So we could factor this as, don't forget the 2, that was the initial GCF. But then 3x plus 5 times 3x minus 5. Then I'll give you a minute. Why don't you try this last one on your own? 32x to the third minus 18x. See if you could factor it out. We're going to have to take out a GCF first. What would the GCF be? 2x, right? So if we take out a 2x from this and a 2x from this, we wind up with 2x times 16x squared minus 9. And that is a perfect square like we talked about. 16x squared is really just 4x to the second. 9 is really just 3 to the second. So let's remember the 2x in front. Then we just get 4x plus 3 times 4x minus 3.